Okay, so we'll get started here. Apologies for the delay. Today's lecture, based on some feedback from students and some thoughts about what might take us forward best, I decided that I'd have a little bit more. Okay, it looks like we lost the application sharing here. So let me try that again. I thought we'd have a little bit more discussion of the case of our first order delays to clarify some issues with them and to try to give a sort of unified understanding that of the various factors that I referred to last time. So, within today's discussion, we're going to be talking about first order delays in some more detail, with a particular attention to coming away with an overall appreciation for their different facets. We talked about a couple features of first order delays last time. What were some of the features that we referred to? First of all, why do we talk about first order delays?
One question, why are they called first order delays?
Sorry?
Why are they called first order delays?
Because we're going to see higher order delays today that are made out of first order delays. Okay? These are the basic building blocks of models, and we compose larger sets of structure, and particularly larger what we call higher order delays out of them that allow us to describe processes with additional features. But these are kind of the individual Lego blocks, as it were, or something close to that when it comes to system dynamics models. They're certainly one of the main Lego blocks out of which we build these system dynamics models. Could anyone mention to me some characteristics we discussed about first order delays?
Just a really quick question.
Yeah.
First order delays, do they get their name because of the order of the differential equation?
Yes.
Okay.
That's a lot of the issue. There's a couple different ways you can look at it as a different order. One is with respect to differential equation. Another is with respect to the probabilistic distribution. So it turns out that these delays observe certain statistical properties. They have certain statistical properties with which they're associated, and particularly they relate to something called the Erlang distributions, family of distributions, and they relate to Erlangs of corresponding order. So first order Erlang, second order Erlang, that sort of thing. So we'll see that as well later in the lecture on higher order delays. Okay. So great question. Other questions? Okay. So what were some features though that we discussed last time with respect to first order delays? What were some characteristics that distinguished them?
Dependency on the stock.
Okay, so they exhibited a dependency on the stock. And what sort of dependency was it? They had their behavior over time depended on the value of the stock. And when I say behavior over time, behavior of the flows depended on the stock. And that's characteristic. If the behavior of a flow into or out of a stock depends on the value of the stock, we talk about there being a what? Is it function? Okay, there exists a functional relationship, but we talk, so the value of the stock determines the value of the flows, and the flows determine the value of the stock. We talk about there being a feedback. Thank you. You spared me from a game of Hangman. There's a feedback involved. And what sort of feedback is it that we see with first order delays? It's a negative feedback. It's a regulatory feedback. It's a feedback that keeps the system stable, in which perturbations to it, in which disturbances to it are pushed back against, or forgive my poor English. It resists disturbance. It has an elasticity associated with it. It pushes back against forces applied to it. So if you perturb it, if you add 100 to the value of the stock will come back towards its original value, right? It won't spiral off into sort of ever and ever greater values. Instead, it recovers. It has this resiliency, this robustness. Sort of like other cases of negative feedback that we first discussed, cases of homeostasis. We get cold and our body has ways of ramping up the metabolic rate so that we're warmed again. We get hungry, we go eat. We get thirsty, we go get a drink. And in all these cases, it's a regulatory feedback. It kind of keeps us in balance, right? It keeps our water balance, keeps our salt balance, it keeps balances of other electrolytes and of energy and all these other different factors. Our body is just filled with these regulatory processes. And you can think of a first-order feedback as kind of the simplest version of these regulatory processes. Okay. So that's good. That's one property of a first-order feedback. What's another property of a first-order feedback? It reaches an equilibrium. It comes to some long-term stability. So it's stable around a certain point. It tends back towards this equilibrium, towards a state of balance. And if it's knocked off of it, it tends to recover that balance. So that's good. It's another feature. Well, I said that it exhibited a memoryless character. Wow, that's a mouthful. So here's our first order delay that stands in front of us. So we have this inflow, and then we have an outflow, and the formula here, if we specify it with some mean time, some time constant delay. What's the formula for this outflow? Stock over mean time delay. Those of you from physics or engineering background, your mind should just pull you towards dimensional analysis to understand this. If we have a stock and it's measured in units, some units X, units X associated maybe with persons. What are the dimensions associated with the inflow and outflow? How do we what sort of types of quantities are they?
Persons per unit time.
Persons per unit time, right? And if we have a formula here for a flow, therefore it has to return a value that's in persons per unit time, say, right? And so if you have a delay, it's got to be the stock divided by the delay. It can't be times the delay. Then the flow would be of units, persons times time, which would not be compatible with being a flow of the stock. The stock is the integral of the flows, and so if the stock is of unit X, the flows have got to be X over time in their units. Okay. We'll come back to this issue at the end of the course of dimensional analysis. It's an extremely powerful tool, and it can lend a lot of insight into these models. But the fundamental thing here is that we can often just look at a diagram and say, oh, this is a delay up here. This one up here is a delay, and this is a stock, and it's going into this flow. And if we know the units associated with this has to be units per, whatever this units are per unit time. And so the formula for this is quite obvious. It's this divided by that. Okay, so that's good. Was there another formulation of this that we saw that didn't involve explicit statement of a delay, but it had a different formulation associated with it? We had not a delay explicitly, but a variable that was a rate constant. By rate constant, I mean a chance per unit time of leaving the stock. Remember that? Remember that? So if you were a person in the stock, you would have, say, 1% chance per month of leaving the stock, or 1% chance per year. Okay. Ladies and gentlemen, especially those from the physical sciences, what would the units of that rate constant be? First of all, what's the formula for this rate constant? If we have a rate constant, a chance per unit time of leaving, Well, okay, tell me what units that's in. A chance per unit time.
1 over time.
1 over time. It's like a fraction. If I said the fraction of this floor that's, covered by this desk or something, that's independent of units. It's of unit 1. It's independent of unit choice. And so it's fraction over time. The fraction of people that leave per unit time. So that rate constant would be 1 over time. And so the formula for this has just got to be what? Oh, man. Come on, tell me, folks. Okay, so if we have a rate constant, it's some number, its dimension is 1 over time, and we have a stock, and we know the value of the flow depends on the stock, something involving the stock and this rate constant. With units 1 over time, it's got to do what? Oh, it's got to multiply them, right? Okay, the flow. Okay, so if we have a stock, and the units of that are, say, persons, right? And we have flow out. The units of that are persons per unit time. Let's say persons per month, okay? Persons per month, yeah? It has to be. It has to be person. This stock is the integral of this flow. You sum it up over many months, you get a number of persons. So whenever you see a stock that flows in and flows out, it have to be the units of that. The units of the flows have to be the units of the stock divided by time. Always is the case, okay? Okay, so now if we know the formula, there's some mystery formula here involving the stock in unit persons, involving some rate constant, which is a chance per unit time of leaving, that's got, say it's 1% chance per month of leaving. That has a unit associated with it of what? Of 1 over time. And so this is 1 over month, chance per month, likelihood per month, fraction of people who leave per month. A fraction of something is dimensionless, so we write its dimension as 1. It doesn't depend on any dimension. I could measure this floor in square meters, square centimeters, and square feet, and the fraction of it occupied by this desk is still the same. It's independent of units, so we say it's 1 over month. So look, if we have some formula involving the stock, measured in persons, and this rate constant measured as whose unit is 1 over month, it's just got to be the multiple of them. This is a rate constant alpha, this is a stock x, and the formula here is alpha times x. What's the unit of that going to be? Persons per month. You multiply something of unit persons times something of unit 1 over month, you get something persons per month, okay? So these are two different ways of formulating the same system. They're just two different lenses, or two sides of the same coin. They're equivalent mathematically. What's the mean time, if we have a rate constant, we say 1%, people have a 1% chance per month of leaving the stock. How long do they spend in the stock on average? They spend, I have a 1% chance per unit time, per month in this case, of leaving. On average, how long do I stay? Yeah, 1 over 1%, or 100 time units. Okay? Yeah? So I could have expressed it as the number of persons in the stock divided by 100, or I could have expressed it as the number of persons in the stock times 1 over 100. You see how those are the equivalent? I could express it as x divided by 100, where the 100 is the mean time until, so I could express this as, the value of a stock divided by 100, where 100 is the mean time in the stock x, right? Eh? so can express the flow out of the first order delay as x over 100, or I can express it as x times 1 over 100, i.e. x times 0.01, where 0.01 is the chance per unit time of leaving, right? You see how they're the same. I mean, they're just restatements of it. We're just relabeling the things. We can call it divided by the mean time, i.e. 100, or times the chance per unit time of leaving, i.e. 1 over 100. If you have a chance per unit time of leaving of alpha, the mean time you spend in the stock is 1 over alpha. Good. If you have a mean time in the stock of tau, the chance per unit time of leaving is 1 over tau. Good. These are two different sort of views of first order delay. Now the key thing here, folks, or a key thing, is that it's memoryless. It doesn't care how long it's been since you came into that stock. You might have come in a long time ago, or you might have come in a brief time ago into this stock. Your chance per unit time of leaving is the same. You have the same kick at the can. As long as you're still in that stock, you have the same chance per unit time of leaving. That's also a feature of these systems, of this sort of building block. It's memoryless. We're going to build pieces out of it that are most certainly not memoryless. The higher order delays are not memoryless, but this individual piece is. Okay, and it affords itself some simplicity of reasoning. So those are some features we talked about. And actually I have a set of review slides that will be coming up to cap it all up, where these things are reviewed further. Okay? But any questions about that before I talk about some additional features to help you understand why it's called a first order delay? Okay? Okay, ladies and gentlemen then, let us look at just a few other features of it. I asked you, I suggested that you actually do a little homework. I asked you to phrase a little problem such that you had a stock into which came an inflow, which was 0 for a while, and then it rose suddenly to a value, say 1, or a value 10 in this case, or sorry, 20 in this case. So it went from 0 over here to, boop, at time 50 went to 20. And I asked you, what would the stock do in return? What would the value of the stock do in return for that? Suppose the stock started empty. What is it going to do in response? Stock's empty. If a stock is empty, it's a first order delay. What's the outflow? The stock is value 0. What's the outflow? 0. Good. And the inflow is 0, so the stock just stays empty. Then suppose suddenly the inflow is 20. What's going to happen to the stock? Sorry? It's going to start filling up. The inflow is greater than the outflow, so it's got to start filling up. Good. So it starts rising. And its rise looks just like this. But the rise of it, it's rising up to a value, an equilibrium value, that may be very different from the value of the flow. I mean, they're actually, it's not really meaningful to compare one with the other because they're in different units. The flow is in people per month, and the stock is in people. We can't really compare, say, one bigger than the other. They're in different units. It's like trying to compare a centimeter to a second or something. It's like, it's nonsensical. 1 second is not bigger than 0.5 centimeters. That's meaningless. So here, what I've drawn is actually the value of the stock and the value of the outflow to the stock. How would the value of the stock look? Anyone? What would the value of the stock look like? What? Okay. I heard some encouraging muttering. Mutter more, young folks. Yeah, it's going to be linearly dependent on this. It's just going to scale this in some way, right? But the outflow is just the stock times something or divided by some constant. So it's just like this. It's just on a different scale. I mean, we'd have to plot it, on a different graph or with a different scale because we can't really compare them meaningfully. But it would rise up just like this. It would rise up fast initially because it's filling up more quickly, but it's going to eventually rise up slower and slower. Why? Because, the outflow starts picking up. It starts losing stuff going out, so it's going to be rising less quickly. The gap between the inflow and outflow is becoming less pronounced, right? Okay, but what I've drawn here is the inflow and outflow, which are dimensionally comparable. We could talk about comparing something that's in people per month to something that's in people per month, right? Okay, and what do you notice? If I didn't interfere with this at all, I just changed that inflow to 20 and I just let her rip and she just kept on going as long as wanted, what's going to happen to the outflow? Where is it headed? Sorry? Okay, yeah, and why is that? Why is it headed to the inflow? It wants to reach equilibrium. There's a very good reason, because if it's less than equilibrium, if the outflow is less than the inflow, what's going to happen? The stock is going to increase. It's going to increase the outflow. If the outflow is greater than the inflow, what's going to happen? Stock will decrease. There's going to be more going. Stuff is going to be going out faster than it's coming in. The drain is going to be draining faster than the water is coming in. It's going to go down. So it's going to be pulled to it. It wants to reach this equilibrium. So if we let this rise up, it would rise up towards that. And ladies and gentlemen, what will happen if we have different time constants associated, different mean time with infection? How will that change things? Because after all, that affects the outflow, right? The outflow is affected by the mean time with infection. If we have a very, very large mean time with infection, remember the outflow formula is given by the value of the stock divided by the mean time with the mean time, right? The delay. And so if we have a very large mean time in that stock, the value of the flow will tend to be what? Smaller initially, and eventually it will reach that equilibrium. The outflow will reach that same equilibrium level. It'll just take a longer time to do it. Okay? And we'll get something like this. This is with different values of alpha, but you can phrase it as different values of the delay, of the time in the stock. So what you're starting to see here is some aspects of why this is called the delay. What's going on here? Well, the outflow looks kind of like the inflow, but it's delayed and smooth. Do you see that? So the inflow kind of went up and it shot up at 50. It was like not a square wave, but we call it a Heaviside function. So I think the term of art for it. It goes and it rises up and it stays up, right? It's a step function. This is a more colloquial term for it. So it rises up and stays up. And you'll notice if the delay is longer, it's kind of smoothed out over a longer period. If the delay is really quick, it sort of rises up. And it's actually quite similar in some ways to what we see as the input. But it rises up. And in all cases, it's exponential. We see these things a lot in engineering. The formula for this would be like 1 minus e to the minus alpha t, right? And the bigger t is, the smaller and smaller this e to the minus alpha t is, and the closer it's going to come. Okay. This is for the flow. What does the stock do? Well, the stock also rises, but it rises to different levels. Why? Why does it rise to different levels? I mean, after all, with these different delays, the outflow rises to the same equilibrium, right? Do people grok that? Grok or not? Grok. So here with the outflow, it always, no matter how long the delay is, as long as it's some finite quantity, it's going to be going to the outflow eventually, right? It's going to eventually reach closer, arbitrarily close to the outflow. It's going to get closer and closer and closer, right? It's the nature of the beast. The inflow is greater than the outflow, so more is going to accumulate in the stock, and so eventually the stock's going to have such a level that the outflow is going to be approaching the inflow, and it's going to be slowing down, but it's going to approach it, and the same is true from above, too. If it was too much, it would come down. Okay, that's great. That's great. But what is the stock doing? Well, the stock's going up to different levels. Why? So the outflow is going to this. It's like a delayed version of the inflow with more heavily smoothed or less smooth, depending on this time in the stock. But why is the value of the stock going to different levels?
Depending on the stock quantity.
Yeah, exactly. I mean, if the outflow is the stock divided by 1 million, the stock's got to go to a much higher level to make the outflow equal to the inflow than if the outflow is the stock divided by 2, something like that, right? Does that make sense? Okay. Sense or not? Okay. So it's got to get up to a much higher level. The value of the stock rises, and you notice it rises at different speeds. This is with a really long delay. This is with a short delay. Why do we see this? Well, the longer time delay requires X to be larger to make outflow equal inflow, for it to reach equilibrium. Does that make sense? Okay, good. Okay, so, outflows here we view as delayed version of inflows. This is one reason we call it first order delay. Okay, the output is a delayed version of the input. Okay, so here we have sort of different delays. This is 2-year, this is 5-year, this is 10-year, and this says 10-year as well. So I'm not sure. Okay, and if the stock doesn't start empty, then it will decay, say at first, and then rise. Decay at first if there's no inflow, and then rise as inflow comes in, and so on. So that's great. So there's goal-seeking behavior going on. The outflow wants to kind of be equal to it's pulled to be equal to the inflow. Okay, and it's associated with the negative feedback loop. The larger the population of the stock, more people die, for example, per year, and there's goal-seeking on the part of the stock. We could view it as goal-seeking on the part of the outflow as well. Okay, if we have more people coming in that are going up here, the stock rises to the point where inflow equals outflow. If we have fewer people coming in that are going out per year, then the stock declines until inflow equals outflow. Does that make sense? So it's kind of optimizing for this balance. So we have some rate of inflow, there's some surplus that increases the stock, and that leads to a higher rate of outflow. So there's this negative feedback involving outflow adjusting to inflow. Does that make sense? Okay. This is another way to view it, and you'll see first-order delays depicted on this. We're almost done with the basic understanding of first-order delays here. So we can phrase them. We've been concentrating on the phrasing on the bottom here. Okay? The phrasing on the bottom, we are phrasing this thing as, okay, we have some delay, and we have some outflow. And in this case, I happen to phrase it as a delay rather than a chance per unit time. Two sides of the same coin. This outflow here has a formula x over delay, right? It's just got to be, because the units of the flow are whatever units of this divided by time. So if we have a delay and measured in time and an x measured in whatever units it is, persons, this has got to be persons divided by delay. This has to. You wonder why I'm telling you this over and over again. It's because I see the exams.
Because I see the example and the students got it wrong. Oh, please, just go back to this habit of thinking about, okay, it has to be the case dimensionally that those fit together though. Dimensions are beautiful. They structure the world. They require things to be certain ways. There's a hidden order that comes out of the dimensional structure of the world. And you're not really taught about it as an undergrad. And you're rarely taught about it as a graduate student. But if you really understand it, you can do extremely powerful things. And one of the most prosaic things you can do, the most basic things, is just check your model. Just do an eyeball check and say, can this be reasonable? You can do much more powerful things, but that's a basic feature. So here, folks, we have this x over delay here, right, as the formula. And we can phrase things like this. We have some inflow, we have some outflow that's divided by delay. And that's great. And ladies and gentlemen, remind me again, speak, hopefully as if in a Greek chorus. What will be the equilibrium value of this stock, for speaking about the one on the bottom here, confining our attention to this, which is the formulation we've been talking about. What's the equilibrium value? If inflow is constant, what's the equilibrium value of x? Inflow times delay. It's got to be, because at a value of x, which is given by inflow times delay, what's the value of the outflow? Let's say that again. So what's the characteristic of equilibrium? I'm asking, what's the equilibrium value of x? What's the value of x that the system wants to achieve? What's the value of x at which it will be in balance and stasis? We can phrase it all sorts of ways. And the answer was given is that it's correct. It's delay times inflow. What's the quick way to check that? You plug it into the formula for the outflow. At x equals inflow times delay, if x equals inflow times delay, what's the value of the outflow? Yeah, inflow times delay divided by delay, which is just inflow. So it's got to be the case that the equilibrium value, you plug it into the outflow and you get the value of the inflow, right? So do you see that? Okay. Some of you probably wonder why I get so excited about these things, but I suppose it's one of those mysteries. It's because it's so important in appreciating what's going on in terms of the dynamics down the road in just a few lectures. If you understand this, if you grok it, you will start to grok what you see much more deeply. Okay, that's great. So we can phrase it as this bottom one. But another way to phrase it, ladies and gentlemen, that may be even more intuitive to you, is at this top thing. This is also a first order delay. This is your friend, the first order. I hope it's your friend. It's my friend. And I hope it's not your enemy anyway. This is the first order delay up top as well in a different guise, with a different mask. So I happen to have labeled the stock X2 here, just so we could see them in the same diagram. And we have a single flow, and you can think of it as kind of a net flow, okay? And here, the formula for the flow at the top here is some target, and that's the target for the stock value, minus the value of the stock quantity divided by delay. So in other words, in parentheses divided by delay. So it's these and this minus this divided by delay. And that's the value of the flow. This flow could be negative or it could be positive. And you'll notice X target is part of it. That's the target value for the stock. Can anyone give me some intuition why that formula?
Well, the greater the difference between the value of the stock and the target value, the
Yeah.
greater the flow will be.
Good. Exactly. That's exactly it. So let's use as a archetype. Suppose that the value of the stock equals the target. What's the flow going to be? 0. Ladies and gentlemen, we just showed that the equilibrium value for the stock is what? Is the target, is X target. In other words, that by definition, that's the value at which there's no flow in, no flow out. The stock's in equilibrium. There's no change to it. The flow is zero, and a flow of zero occurs when x2 equals X target, right? Suppose that x2 is below X target. What's going to happen? Then this formula is going to give something in its numerator, this X target minus x2. If x2 is below X target, it's less than the target, then the flow, this difference is going to be positive, right? And it's going to be flow into the stock, and the stock value is going to increase. And that's going to bring it closer to the target, to its equilibrium value. On the other hand, if x2 is too large, this thing in the numerator is going, when I say too large, if it's above X target, this thing in the numerator is going to be negative, and so the flow is going to be, net flow is going to be out, and so it's going to bring x2 down, right? So here, with target, we can sort of set the value of the stock towards which it's sort of tending. And so this is another form in which you see a first order delay. They're equivalent, ladies and gentlemen, if X target equals the equilibrium value as we specified it earlier, delay times inflow. I mean, these two are basically the same. If you plugged in X target as delay times inflow here, you just divide by delay. What you have is X2, you have inflow minus x2 divided by delay, which is exactly what you have here. Yes, the net flow. So anyway, these are two different ways to write a first order delay. Does that make sense to people? The top one is in some ways more familiar or more comfortable in the sense that it's following this target, and the negative feedback is quite clear here because you have X target minus x2. How if in the exam you couldn't remember, is it x2 minus X target or X target minus x2? How would you reason that through?
X target should be positive.
X target should be positive. Okay. Yes, okay, so the larger X target, the larger should be the flow in, for example. That would be one way to think about it. Another way, folks, is if it were x2 minus X target, what would happen if x2 were bigger than X target? It would get even bigger, right? The bigger it got, the faster and faster the flow would occur into it. That doesn't sound like a negative feedback loop to me. It isn't pushing back against being nudged. It isn't, if you perturb it, if you push it away, you push it bigger than X target, it's not going to push back. If it's x2 minus X target. In fact, it would just amplify it. But here, if you increase x2, if I were to go and I were to dump a thing of water into my bathtub, or I were to inject a value and increase the value of x2, it's going to resist because now maybe x2 is bigger than X target, so it's going to have a negative flow out, it's going to flow out, and it's going to be brought back down. It's going to be brought in equilibrium. Does that make sense? Okay, so we've just seen first order delays more. Now, let's talk about first order delays, and there's one thing I realized I need to put in here, which is first order delay. So leaving the stock is independent. Chance of leaving the stock is independent of the length of time that have been in the stock. So this is what we call memoryless. Okay. The process is memoryless. It doesn't matter how long we've been in that stock. We have the same chance of bringing it time. So, summary of first order delays. They're regulated by a negative feedback loop, and that means they're stable. They push back against disturbance. We saw it last time, right? We perturbed it periodically with this event, just just added 100 to it, and it kept on going back to its value. It just kept on returning to its value, kept on coming on. It involves involves a typically constant coefficient of some sort that can be phrased in one of two ways. We can phrase it as basically a stock with a flow out. So the flow out. Sorry, I should have made that clear. The flow out involves a typically constant coefficient phrased in one of two ways. It could be, the flow out could be the division of the level of the stock by a time constant, specifying the mean time spent in the stock, right? So we have persons divided by months, so it's persons per month. Yeah? Or it can be multiplication of the level of stock by rate constant. Persons times chance per month of leaving. Again, dimensionally correct. It would be persons per week, or persons per month. Okay, as the value as the units of the flow. Okay, for given a constant inflow I, the equilibrium value is at I times this time constant, or I divided by alpha. It's got to be. It's got to be dimensionally. You look at it. I, what's its time? What's its units? What are its dimensions? Let's suppose we have persons in month. What are its units? I is measured. The inflow is measured in persons per month. So you multiply persons per month times months, the time constant tau, and you get person. Or you can take, alternatively, if you have a rate constant alpha, chance per unit time of leaving this stock, a kick at the can. You have the inflow, which is of units, persons per month, divided by something that's of units 1 over months, and so you get persons. It's beautiful. It's consistent. Okay, so alternatively, we could specify a first order delay as a stock with an inflow and outflow, depending linearly, with an outflow that depends linearly on the value of the stock, based on some delay, or multiplied by a rate constant. We saw that. Or it could be specified just like we've just seen, as a stock with a single net flow whose value is given by the value of some target minus the value of the stock, all divided by some delay, or all times some rate constant. Though traditionally these are done with delays, as the preferred way. So the equilibrium value, we just said it, and it's memoryless. The chance of leaving the stock is independent of the length of time you've been in the stock. That same chance, and it's viewed as well mixed from a chemical engineering perspective. It doesn't matter how long you've been there. The kind of set of people in the stock, they're similar enough that we don't have to reason about how long they've been there. It collects a similar sort of set of individuals from the perspective of leaving, their chance of leaving. Okay, first order delays. Make sense? Okay, great. Okay, that's fantastic. What I'm going to go on to now is we're going to take a look at aging chains and higher order delays. Okay. Talked about the principle earlier that system structure shapes behavior. So the behavior of a system like this is shaped by the presence of stocks and flows and the connections between them, and most notably feedback loops. Feedback loops are not merely interesting curiosities. They have a profound impact on the behavior of a system. I used the example before of the yardstick which we balance, right, on my hand. And I argued that the behavior of that system is profoundly different if the feedback involved is cut by closing my eyes. Okay. Our ability to manage our own, keep our body in healthy shape is fundamentally governed by the negative feedbacks involved. Without that, we would, we'd go out and wait for the bus and we'd be dead. right? Something along those lines. We'd be at real risk. When governing feedbacks from a health perspective are challenged, we greatly suffer. We need things that artificially ventilate us or what have you. So, in all sorts of systems, feedbacks end up being a fundamental shaper of the behaviors. We'll see that nonlinearity plays a big role in this, and stock and flow structure and delays associated with it. We're going to get to linearity maybe next time. I want to talk today about the higher order chains and competing risks. Okay. So the issue with the higher order chains is we often want to move beyond a memoryless assumption here. So the idea here is that in first order delays, we're assuming the chance per unit time of leaving this delay of the structure is independent of how long we've been there, right? I phrased it here a little bit more precisely. The per unit time risk of transitioning to the outflow remains equal no matter when one entered the system. No matter how long is from when you entered it, you're going to leave. But we often know that transitions in the real world are not memoryless. Our chance of dying is not independent of age. Our chance of developing end-stage renal disease is not independent of how long we've had diabetes. Our chance of developing AIDS is not independent of how long we've had HIV. They're not memoryless. We don't have that same chance per month of developing AIDS all throughout HIV infection. And so often, there's fundamental sort of series of underlying processes which go through stages. They go through successive phases, and we want to capture them. And so, ladies and gentlemen, we do so perhaps at a certain philosophical level. It may seem a bit paradoxical, but we can build structures that are memory full, that are not memoryless, where we have very different chances of leaving per unit time, depending on how long we've been there. We can build that up out of pieces that are memoryless. Okay, we can capture different levels of delay using cascaded series of first-order delays. And we call the delay resulting from such a series a kth-order delay. Okay, so if we have two of them, we call a second-order delay. Three, we call a third-order delay. And the behavior is just a reflection of the behavior of the sub pieces cascaded together. Okay, so to understand this, what we're going to do is we're going to show something about the behavior of a kth order delay, say a third order, or fourth order, or fifth order delay. But we're going to keep constant the total time across the system. Okay, so we can kind of reason apples to apples. We'll kind of say, suppose you have a total time to transition across the system, an average time to transition across the system, 1 month. What would it look like if you had a first order delay, a second order delay, a third order delay, a fourth order delay? Okay, so here's our first order delay. Here we don't even have an inflow. We have this some initial value, and then we have this outflow, which is the value of the stock divided by this mean time until death. Familiar? Okay, good. Okay, so here, your chance of leaving is independent. Given that you haven't left the stock yet, your chance of leaving in the next time unit is independent. However, a lot more people leave early than leave late. Why is that? If you started with 1,000 people here, why do I say a lot more people leave early than leave late? Your chance of having left within the first month is much higher than your chance of having left in the 100th month. Why?
Because the outflow is dependent on the value of the stock, and it goes down over time.
That's right. It goes down over time. So if you're still in the stock, you have that same darn chance every successive month. But initially, there's a lot more people there to leave. And second of all, you're in order to stay for the 100th month, you've got to have missed leaving the first month, the second month, the third month, which is very unlikely. Given that you're there, your chance per unit time of leaving
each successive month yet is the same. It's just unlikely you would have lasted that long. So, if we were originally in the stock, our chance of having left it in the course of a given time unit, say left it in the first month, or having left it in the second month, or having left it in the third month, etc., it's declining. So the number of people in the stock goes like this, and your chance of remaining in the stock goes like this. And your chance of leaving the system, here's the system is just one stock. And here we have a chance of leaving that's the same, and so your chance of leaving goes down like this. The chance of having left in a certain time unit from the system. Does that make sense? Yes?
I don't understand why delay is being so seemingly confused with equilibrium. They seem like they're semantically very different, and it seems like we're talking about like first order equilibrium behavior. I don't understand why it's like if it's delay in the system, that just means to me that it's going to take a while for the effect to come in, but it actually seems to mean that it's tending towards this equilibrium.
Well, it is going towards an equilibrium, but that's because here we're just, maybe this is an artifact of how I've set up the situation. I wanted to look at a situation which was common across all of these, and I'll be coming to the later ones in just, within another 30 seconds or so. But the idea is that we have some group of people that start, it's as if they've come into the system at time 0. They're in the stock, and we want to see sort of when they're going to leave the system. So it's as if and we're interested in seeing when they're leaving this system, say via this outflow here. And this is essentially showing how many are leaving per successive unit time. Are you in sync with that, or?
Follow so far.
Yeah. And we're going to be doing that for successive types of delay. So if we chain these two together, for example, so we have one after the other, when do those people tend to leave the system? And it's quite a different profile. This is quite different from this. And this is a second order delay. And here, this is a third order delay. It's different. Yeah, and I'm going to be highlighting those differences. But the question is, if we had people coming in all cases, suppose we had people coming in at this time 0, when would they be leaving? This is what it depicts. It's as if they're starting at time 0, they're starting in that stock, they're starting coming in, when do they leave? That's what we're trying to examine here. Does that make some sense? Yeah. Okay, so here, this is when they'd leave from a first order delay. If they were to come in here at time 0, all as a group, this is when they'd be leaving. Here, for a second order delay, why aren't they leaving immediately? Why is it? Well, what's the big difference between this and the first order delay? Anyone? What's the big difference? Starts at 0. Why does it start at 0?
Delay of the delay.
Yeah, exactly. So people come in here. We could conceptually think of people appearing here at time 0. And there's very few that are going to be able to rush through here, right? It's going to take some time to go from here to here, okay? And again, remember, I'm trying to keep constant the average time till they get out across all stages. So each of these stages has an average time of transitioning it. Each of these two stages, the average time of transitioning it of half the time of this one. So the total time is still the same, but here, they come in here at time 0, and you're not going to have people immediately leaving. They got to go through the second stage. Even if they quickly go out of here, they're going to likely be delayed here. So there's very few people leaving initially, but pretty soon you start to see the pulse go up and then come down. Okay? Does that make sense? Okay, let's try a third order delay. And I want you to tell me what's different between this and a third order. Take a look at this. Okay, study it carefully. Here's a third order delay. What's the difference? Both are kind of peaked like that. Great. But what's the difference between them?
The peak is later in time.
Peak is later in time. That's true. This first one has to peak immediately, right? Like, people, the most likely time for someone to leave is very quickly after it starts, right? That's the most likely time.
even though they have, if they're still in the stock, they have that same chance of leaving, that the most likely time for them to have left is initially. Here, it's later, something like 10, right? Here, it's later yet. It's something closer to 12 or 13, something like that. And another thing you'll notice is that there's something different going on here at the beginning. What's different? Here it's actually immediately rising in almost a linear sort of fashion, very steep. Here it's not. It actually takes some time to sort of wend its way up. Okay? And so it's rising more slowly at first and then winding its way up. And if you look at higher order delays of successive order, here's the first order delay here in the sort of magenta, and then a second order delay is this black one here. Third order delay is gray. Fourth order, and you find it getting more and more pronounced here, more and more of a sharper sort of spike. You notice also the peak here is growing. More and more people are getting concentrated to leave within a smaller time frame. For those from engineering background, this may remind you a little bit of what's called the Dirac delta function. I don't know if any of you folks have heard that, written as delta of t. And the argument for that is you sort of consider a limit as you go from sort of a square box of width 1 and height 1 to something that's of width half and height 2 and width a quarter and height 4. And in fact, it's a very similar thing here. An infinite order delay, it turns out, will lead to them leaving exactly that amount of time later. Okay? The more and more delays you get, basically, here, strung together, as long as we keep the total time constant, as long as we're adjusting the time of each sub-delay, so if we have k delays in a row, we have time for each of 1 over k, so you come out in time 1 total. So we're keeping constant the amount of time. It gets closer and closer to an impulse. In other words, if people were to leave exactly, in this case, I think it's close to 20 time units after, then it would be an impulse. Just, no one would leave before it, and no one would leave after it. They'd all leave at time 20. And that's what these are approaching eventually. But we are stringing them together in longer and longer series, so going from second to third, etc. Now, it turns out that that as we reduce, as we add in stages, we reduce the time to keep the total time constant, and as we let k go to infinity, the distribution of time to leave the last stage approaches actually a normal distribution. And if we keep the total time constant, impulse an impulse function. Okay, so this is getting closer and closer to sort of a normal distribution. And for those who have a stronger statistical background, some will recognize this as what are called Erlang distributions. These are Erlang distributions, Erlang of order k. So this is definition of an Erlang distribution. So one's like the chance of having left a certain amount of time later is given by these Erlang distributions. Okay, and k equals 1 is the exponential distribution. So we have these successive delays that we can string together, and occasionally you'll define these to capture a certain distribution. But often you want to just represent it because you want to represent stages of things. So for example, here's a model of successive stages of kidney disease. So you have stage 1, stage 2, stage 3, stage 4, stage 5, kidney disease. And you sort of string these together and you treat each as a first order delay. This is extremely common in this sort of modeling. Or you have stages of progression of infection. So for HIV, for example, you might have an acute phase of HIV and then some successive phases. and then a stage of AIDS. And each of them you model as a first order delay, and you string them together to capture sort of the progression between these. So in system dynamics modeling, building up structures of first order delays, possibly with competing risks effects like we saw earlier, allows us to capture these processes which involve staging. A key thing here is any one of these, if we consider people coming into this, their chance of having left on a certain flow, if we ignore the competing risks effects for a moment, their chance of having left after a certain amount of time, conditional on still being in the state, is independent of how long they've been there. For the entire system, it's definitely conditional on how long they've been in the system. Okay, so these are higher order delays, and we build these up all the time. So if you were thinking about mosquito life cycles, for example, you might have stages like eggs, larvae, pupae, and full-blown mosquitoes. Or you might have, for people, you might have, infants, and then children, and then young adults, and then, so adults, children in education, and then possible secondary education, and then those in the working world, or something like that. So you often will characterize a system as divided into these compartments, and you'll have what are called aging chains. Not because it always represents chronologic aging, but because it represents staging, it represents phases of a successive system. And we represent these with these delays. Any questions about that before I just hit on briefly the issue of competing risks? Yes?
Earlier you had a slide that said something about K.
Yeah.
First order delays in the meantime.
This one here?
Yeah. The first jot there, that's assuming that all the stages have the same mean time.
Yeah. For this illustration, it doesn't have to be. I mean, for example, with this model, they had very different lengths for each of them. But for this particular illustration, for clarity, I adhered to. So this was specifically referring to the example I was showing. The mean time of K stages here is just K times the mean time of one stage. So they were all uniform here, and I want to illustrate the distributions associated with it. So here they're all the same. In general, they're not going to be the same. In general, most models, if you have these phases, some phases may last for a long time, some phases may be very brief, and you're not going to get this additive effect. Here you will, though. Here you will, for the particular example I gave, to try to show how the behavior of a kth order delay differs as K varies. I wanted to compare apples with apples, so I want to have a situation where in all cases they have the same mean time to transition across them. Believe it or not, all of these exhibit the same mean time across them. They exhibit different variants, but the same mean time is conserved. It's invariant. And I wanted to capture that, and I wanted to make it, for simplicity, so that they were all sort of uniform subpieces, so I didn't have to make any sort of arbitrary assumptions about which were greater than which. So I just made it the same. It's a mean time to transition across all stages, some stage count, and this gave mean time to transition across a single stage of this divided by that. Does that make sense? That's for this particular case. Yeah. So you're absolutely right, and this is specific to that case. In our examples, we added stages and we reduced this. But this is more general fact. Okay, and you'll see that coming out of there. We talked about competing risks before, so I don't know that I have to deal with this further, but it may be worth noting that that we have these effects by which the mean time to leave on this flow is affected by the rate of this flow and vice versa. And we talked about that before. So in other words,
my chance of going down this flow is affected pretty significantly by if this is, as you have no chance of going down this flow versus if you have a very high chance, the mean time it will take me to go down this flow is affected quite a lot. Okay? Okay. Good. Okay. That's all for that. Maybe I'll make one other comment here, which has to do with the third component of this, delays and oscillations. So we talked about aging chains, and we talked about competing risks, and this is the final component before we go into nonlinear models. All the models we've been looking at are linear, which means that while they exhibit feedback loops and so on, they can be analyzed by dividing things into pieces. We can analyze a given situation by chunking it up into pieces, each of whom we sort of recognize we know how to deal with. We can figure out how it responds to those pieces, and then figure out how it responds to the whole. Next time we'll be going on to models where that just ain't possible, where we can't just divide the world up into these convenient pieces, and where we need to numerically integrate things out. The pieces, incidentally, are associated with exponentials, but we're not going to be spending time on that type of analysis. So here, I wanted to talk about delays and oscillations, how they come out of it, because we've talked about feedbacks in a stock and flow sense, and we can begin to see the different types of feedbacks that we talked about in their characteristic behaviors. One of them that we saw early on here was this one here, and we built this together. This was a little first order delay, and we ran it, and we saw this sort of situation. This is the case where we had this perturbation, and we had this sort of characteristic stability. Ladies and gentlemen, suppose now I build a system with a positive feedback loop. Can anyone give me a system, a common system with a positive feedback loop in it?
Population growth.
Good, excellent. That's exactly it. So exactly the one I was hoping for. So here we have some population, and we're going to have a flow into the population associated with births, right? And we're going to have a flow out of the population associated with deaths, perhaps. We could do a net flow, so we'll have deaths here. Now, we'll have some birth rate, right? We'll make this mortality rate here so that it affects death. Mortality rate, okay. And then we'll have some birth rate. So we'll have a birth rate here. Okay, so we're going to hitch this up. So I'm going to connect this, and we're going to have deaths in the mortality rate, and we're going to connect up. What else does deaths depend on besides mortality rate?
Population.
It's got to depend on population. If there's no one to die, then no one's going to die, right? There's no one at risk of dying, no one's going to die. How about births? Well, it depends on birth rate, and then what? When I say rate there, I mean a chance per year that a given person in the population will give birth. And it also depends on population. If there's no one to give birth, there's going to be no births. Okay, great. So what do I have to specify here to complete this? Well, one thing is mortality rate and birth rate. I'll make the mortality rate 1%. And so people have an average lifespan of how many? If this is 1% per year, they have an average lifespan of how many years? 100 years. Good. And I'll make the birth rate 0.02. Okay. So 2% birth rate. Great. And so now what do I need to specify to complete this model? Okay, we have to specify initial population. I'm going to make this population a population of initial population of 100. Okay, and what else do we have to specify to complete the model?
The inflow and outflow.
Good. So the inflow and the outflow are the key things. And so DES, give me the formula for DES. So first order delay.
Population times.
Good. Times mortality rate, right? Mortality rates in units of chance per unit time, and therefore DES times it gives people or rabbits or whatever the units are of per unit time, and then bursts I got to specify, right?
You wrote
Oh,
deaths times.
oh, did I write DES? Oh gosh, thank you. Man. Thank you. Well, unit checking would have checked that. By the way, you'll notice that AnyLogic, like Vensim, does support unit checking. So you can specify units, and you could say check my model, and it will check the dimensional consistency. That's a good thing. And then bursts is population, we'll call it birth rate times population, right? Okay, so we should run this, and what are we going to see? Anyone? Yeah, we're going to see exponential growth. What sort of feedbacks does this have in it, this model?
Both negative and positive.
Both negative and positive. Where's the negative feedback?
Deaths.
Deaths. Where's the positive feedback? Bursts, right? Okay, so you're going to have competing feedbacks here, and which one's going to win out here? The birth rate, yeah. Death rate isn't changing. Birth rate is higher than the death rate, and so we could speed up time here, and now we're getting into, oh man, it's times 10 to the 20th, 20. And so we have unstable behavior being exhibited here. A change, if I went from 100 people to 200 people, it would perpetually change the number of people from then on who are in the population giving birth. It would diverge from the original one, in a more and more magnified way. That situation we saw earlier with a negative feedback. If I disturb it, it's going to forget about, over time, it's going to forget about that disturbance I gave it. It pushes back, right? I nudge it, boom. And it pushes back, it forgets about that disturbance. Here, with positive feedback, that disturbance is going to continue on. It's going to grow, in fact. It's going to be magnified over time. There's going to be a divergence over time of the trajectories. If I hadn't perturbed it versus if I did. So here we have a positive feedback. One thing we haven't seen, ladies and gentlemen, is the oscillation. And this will be a little challenge to you. We're going to see nonlinear models next time, but here's a little challenge to begin our next lesson. Suppose I wanted to have a situation of a negative feedback. So we have a negative feedback here, but we have a situation where, in fact, I'm going to, what I'm thinking is, I think I'll even phrase it in this other way. This will be even a better challenge for you. So let's go back to it. It's in my other slides here. It's right there. Okay, folks. Consider this situation here at the top. This phrasing of a negative feedback loop. I want you to implement that. Okay? I want you to go, and using AnyLogic, I want you to implement it for next time. But I want to implement it as it is. Okay, great, with an X target, and you can call this X instead of X2 if you want to. That's great. And have this in place. So this top one up here, this guy here. But I further want you to ask the question and at least muse about this, puzzle about it, perhaps implement it. Suppose I wanted to characterize the situation where instead of the instead of being able to adjust this flow immediately based on the value of the stock, so that we reach X target, suppose I instead wanted to represent a situation where we have information about the value of the stock that is delayed, that's imperfect in the sense that it's old, it's obsolete by the time we get it. This is incredibly common. Often we make our decisions about the world not with perfect understanding of the current state of the world, but with understanding that is limited and often outdated. Now, one of the profound effects of information technology in the world is that we're dealing with more and more close to current information, but it's by no means current now. When companies make decisions, they're often still making decisions based on balance sheets computed as of a month ago or 2 months ago. When we make decisions, we're often hampered by our lack of knowledge about the situation right now, and instead we're dealing with a perception based on what it was yesterday, the day before, or even longer ago. So suppose we want to represent a situation where this flow is affected, in short, not by the current value of the stock, but by the value of the stock delayed by a certain amount. Suppose you want to represent a delayed version of the stock and have that affect the flow. How would that change things, is my question. So suppose now you're dealing with a situation where the flow is again affected by a gap, but it's not a gap anymore between X target and the stock itself. It's a gap between X target and a delayed version of the stock. And I would put to you, I would argue to, I would submit to you, ladies and gentlemen, that this challenge should be doable because you know now how to delay versions of things. We've seen delays presented in this very lecture. And so if you wanted to create a delayed version of a stock, you know how to do it now. You know how to make it take a certain amount of time to reach that level. And so see if you could think, it's a little bit of an exercise in recursion here. How would you create a version of this negative feedback system such that it simulates a system where there's a delay between this imperfect knowledge about what the current value of the stock is. Instead, it's delayed. We're reacting based on old information. And I would argue a lot of situations in life are like that. When we drive our cars in ice, we're very much like that. We've made our decision on how much to turn the wheel. The current action we're undertaking in terms of having turned the wheel is based on our perception as of 5 seconds ago or 2 seconds ago. And sometimes that makes a big difference. So I would like you to try that. Puzzle about it. And come here if you can with your attempts. And we'll discuss them, and then we'll get into the intriguing issue of nonlinear models. Models which defy our attempt to understand the behavior of the whole based on the behavior of the parts, and where we'll see much richer behavior yet, which builds on the knowledge that we've built up the past 2 lectures. Okay. Thanks very much. Any questions about the assignment right now? Yes.
I kind of got to come over. I was going to ask, so for question 2.
Yes. Question 2. Yeah.
Yeah, question 2.
Yeah.
It gives you like an inflow and outflow.
Right.
And then you're supposed to figure out the value of the stock.
Of the stock.
You can use math to like just integrate the flows.
You're welcome to do that. So for problem 2, you can do it a number of different ways. I'll accept all of them. You can do it by hand. You can do it, and greater precision is welcome. You can do it by a formal mathematical analysis. You say, okay, this is linear, and that we know the integral of the linear quantities, the quadratic, what have you. You could do it by programming it into any logic or Venn sim and simulate it out.
Yeah.
Any of those ways are fine.
So my question is that the integral, so we have a net flow of t minus 10, or t minus 30. We want to make it different than the sign.
The net.
If the net flow has t in it,
Yes.
then the integral
Yes.
is going
Yes.
to have t squared over 2 in it.
Right.
And
Yes.
I just can't
that's right.
conceptually figure out why it has that over 2 involved. Because if I was thinking,
Mhm.
well, the stock starts at 100, it's going to be 100 plus t times the flow. But it's actually 100 plus t times, or t over 2 then.
Okay, so if we have a flow like this gets into calculus, right? So if this is time t, right, and we have some flow here into a stock where the flow is given by alpha t, for example, right? And if alpha is large, the line is steeper. If it's smaller, it's a less steep line. It's a shallower line, right? But it's rising over time. Then the question is, what is the stock? So here we have a stock, and this is coming in, and it's given by this guy here. So we're going to have a value of the stock. Let's suppose that the stock has some initial value. Call it x0. We'll call the stock x. And we'll call the initial value x0, right? We're going to have a situation where this is integrated, and so the value of the stock is essentially, and the value of the stock at time t is going to be equal to x0 plus the sort of area under this curve, right? And if we want to derive that via calculus, we can do so.
How would you derive it? Like, I know you're simulating calculus, but if you were to just logic it out.
Sure. If you were to logic it out, what I would do is I would say, okay, look, we've got a situation here where we've got a rectangle, half of a rectangle. The rectangle kind of goes over here to the left, so its base is of length t. Its height is of height alpha times t. And so what's the total size of the rectangle? Then we'll get to the size of this what's under the triangle. Total size of the rectangle is the width times the height is that gives for the entire rectangle. That's how much is in the rectangle, which is alpha times t squared. So if we want to reason about the area under this curve, the amount that's flowed into that stock thus far, it's that divided by 2. Why divided by 2? Because this is the diagonal of the rectangle. It's an equal amount sort of on the other side of the rectangle. So it'd be this thing divided by 2. Does that make sense?
Yeah, it makes a lot of sense.
Yeah. So I would think of it geometrically like that. And I think that's most helpful. Because another way to think about it is, look, it's you're getting more and more and more accumulated over time. It's accumulating faster and faster and faster. But the rectangle would represent the situation if it were filling up at its maximum rate all through it. And it's actually only filling up at half of that because early on it was low. Another way to think about it is maybe think about the average value. Okay, the average value over this entire period is alpha times t over 2, right? That's sort of the average value it reached here times t as the length, and so you'd get the same thing there. You get alpha times t squared over 2. Does that make sense? That's sort of another way to view it. Make sense? Other questions? Okay. Good luck with that.
I had to reinstall my. Oh, sorry. I'll let you.
Yeah. I'm just gonna. Bernice, did you hear everything there? Okay, great. The audio was okay. 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 Yeah. You want to ask a question about the assignment? Sure. For problem 2? Problem 3, okay. Right. With any logic. Oh, okay. This is Vensim. Are you on Vensim there? You can use either one, but it sounds like you use Vensim, which is great. So that's fine. So let me go to the assignments here, and you're saying you're getting an error that basically says that no runs are loaded. Is that right? Okay. So is this right after? Were you able to run your model? Okay, so the basic deal is in Vensim, if you run the model, it will create a file that's characterized by this, by whatever run name you do, and so it'll create that, and then you can use a, here, I'll actually show you here on my screen. Can you still see my screen? Okay, so let me just, maybe I actually have a Vensim model up right now. Yeah, here we go. This is a different model, but I could show you. So there's this button up here where I can load and unload runs. So normally, if you run you run this, it will create a run. So test or whatever. It will actually run it, and then it will, having run it, it will allow me to display it. It will show it there. But alternatively, I could go up here and I could load it in. If for some reason it wasn't loaded right now, I can go here and I could double click here, and it will load it. It will load it in. You can control which runs are loaded. Normally, if you run it, it's loaded automatically. So I'm surprised if it's not there. But I would try the control panel, and then maybe you and I could set up a time to look at your screen if you're still having trouble, or I could put you in touch with the TA to do that. Okay, good. So questions here? Yeah.
Yes. Can I get that email again? I just have to do for AnyLogic all the details.
Oh, okay,
the
sure.
Registration and stuff.
Sure.
I can email you tonight just to remind you. But
Sure.
then you uninstall it and reinstall it, and all of a sudden it just lost everything. I was like, oh, that sucks. It's very reminiscent of control systems of EE.
Indeed.
So do we ever dive into the class